Live from the Washington, D.C. area, it's the Emerald Planet. All the ecology news that our viewers want to know. Now, here's your host, Executive Director of the Emerald Planet, Dr. Sam Lee Hancock.
Hello and welcome to the Emerald Planet as we come to you from Washington, D.C. in the United States as we look around the globe in 144 different nations, looking for those 1,000 best practices, the technologies, services, and products that are making a difference as we go through the 21st century. And one of the things we have to be the most concerned about, of course, is water. As we know, around the world, many countries are literally just drying out. Other places, there are massive floods. It's contaminating the groundwater that people actually drink. And it's contributing to sea level rise, as some nations in the South Pacific at this time are actually disappearing. So how do we think about water? How do we access water? And how do we make sure that we have enough good water for all of us to drink? And that's the job of an organization called DC Water. Water is Life in Washington, D.C. And sitting right beside me is Ryu Suzuki. He's a professional engineer, and he's the manager for process engineering, which we'll learn a whole lot about, of DC Water. Water is Life. And Ryu, thank you for being here.
Yeah, it's my pleasure to be here.
Well, looking at this logo here, this is a beautiful logo, DC, the water drop, Water is Life. Tell us a little bit about this, and what does that mean to you day to day as you go to work and you realize that so many thousands of people are depending on you for that drop of water?
No, absolutely. Well, I guess one place where I really learned to appreciate how convenient it is for us to have clean drinking water and a treatment system of my wastewater that I generate is because I served as a Peace Corps volunteer in Panama, and I lived in this indigenous village where there was no running water. I had to go into this little well to grab the water, and I had this little compost toilet made out of a 5-gallon bucket, and then I went into the local creek to bathe myself. So, just the difficulty of not having clean water by opening the tap, I really got to learn about it. So the fact that I'm able to now, as a professional, to serve the ratepayers of DC and providing a good water service makes me very happy.
Yeah, it's fantastic. I've been in 93 countries myself. 60 of those are developing countries, and I've had that same experience. I was on the Sepik River in Papua New Guinea, in different places in Tanzania, way out in the hinterland, and it's the same thing. You may have a couple of gallons for the whole day, and that's going to do everything. You're drinking, bathing, washing your dishes, and all that. But then you come to DC Water in downtown, as I say, in the heart of Washington, D.C.
Absolutely.
And you have this massive, massive facility there.
Yeah.
And tell us a little bit about this. And it's right there. And yet, actually, a lot of people don't even know it's there.
Yeah, absolutely.
Which is quite a good thing.
Yeah, sometimes, especially since we're our wastewater treatment plant.
Yes.
A lot of people prefer to be kind of living a little bit further away from there. But yes, it is a necessary facility for a large society or a densely populated area like this. And what it is it's the largest advanced wastewater treatment plant in the world.
Yeah, so, and I talk about this when I go to countries, India, China, been to Brazil and South Africa and all these places, and I talk about DC Water because as a ratepayer and as a member of the society, I'm very proud of this and all the advanced technologies. So looking at this facility where we are right now, tell us a little bit about what we're seeing.
Okay, so what we're looking at is actually, most of it is our newest facility that you see. It's called the main process train, or it's our biosolids program. So it's one of the byproduct of doing a wastewater treatment plant is you end up with this very large amounts of solids, and it's always been a challenge for practitioners since the beginning to how to beneficially reuse or treat this material. It's a tremendous amount. If you could imagine, we serve 2.2 million people, and
which goes way beyond the border of Washington, D.C.
Exactly,
we might say.
yeah.
It's about 700,000 people. Yeah.
And all that just gets concentrated into our facility. Yeah. Everything that we dump into the sewer system.
But I mean, this looks like just a modern factory location, and then we see the building crane there, and of course, everywhere you go in Washington D.C., you see building cranes. They say that's the state bird of Washington D.C. is the building crane. So we're looking at the site now that we're going to be spending more time about as far as dealing with all these solids. But it's like I've been going there maybe 9 years now to your site. And every time I go there, I see new things.
Yep.
So tell us about the speed and development as far as new technologies coming in and how that's really propelling DC Water to say, we're the most advanced facility in the world.
Yeah, sure. So it's been an incredible journey. I've been working with DC Water for about 8 years. And I feel very lucky because this is right when all this massive construction projects, the capital improvement projects that we call, started. So during that 8 years, I guess we've probably spent close to $1 billion putting in these new facilities. And a lot of it's driven by regulation, but other of it is because it makes sense from environmental and long-term financial and security point of view, which we'll be talking more about, which is the biosolids program.
Exactly. But looking at this old map, the late 1930s, you see fields and some of these separators and all that. And you look at now, I mean, it's just nothing but endless technology.
Yeah.
What is the transition? Now, you've been there 8 years. But I mean, some of the history. And it's just been incredible. The 9 years I've been going there, the transition has been going on that I've seen. But you look at this from the late 1930s, it's incredible.
Yeah.
I mean, it's a whole different universe.
And once again, a lot of this, the one number that I heard is that throughout the lifespan of this facility, DC ratepayers have invested over $4 billion.
$4 billion with a B.
Yeah.
That's
it's the
real
numbers
money.
that I've heard on the lifespan of the facility. And a lot of it is driven by regulation. So back in the 30s, it was just very basic treatment.
Right.
And it went into the river, and a lot of the quality was not as bad, not as great. You certainly don't want to be swimming in what was coming out of the water then. But now, with just all the investments that we have made over since the beginning, our effluent is very clean. Say if you take our effluent water and compare it next to a normal drinking water, it's not to a drinking water standard, but you wouldn't be able to tell the difference.
Yeah, as just far as the visualization.
And
the whole thing about it, this is just like with the Anacostia River, which is a major tributary going through Washington, D.C. They want to be swimmable and fishable.
Yeah.
That's really their category. And that's the same for the Potomac, correct?
Yeah, absolutely.
Which is the major river going through Washington, D.C. But I tell you, it's just looking at this facility. Now, I know you were, this is a very busy slide, but I know you wanted to talk about this schematic and all the things that are going on there, because you see all this massive amount of technology there. But what is happening in all this?
Yeah, so I'm going to give you a very brief version of the basics of wastewater treatment.
Thank you very much for that.
Yeah, so what it is first, if you could imagine, we serve a very large service area going as far as out to Dulles Airport, all DC.
Which is Northern Virginia, and then we're taking in Southern Maryland, correct?
Yes.
Plus Washington, D.C. itself.
Miles and miles of sewer network. So as the sewer travels through the city, it's going to pick up a lot of trash. So the first thing we do is we have these fine screens that just takes out all this, any trash typically over larger than a quarter of an inch.
Got it.
So, and that's key here. So because we don't want all that stuff getting into the downstream process where we have a biological system, and it's just also not good for the equipment itself. So we want to just get rid of all that.
Screen it out.
Screen it out, and that just goes into the landfill.
Right. Okay. And then the next process?
Yeah, the next part is called a primary treatment, and all it is just a circular tank. And if you can imagine, like say, if I take some muddy, murky water and put it into a bowl and just let it sit there for 2 hours, what's going to happen to that murky?
It's all going to settle.
It's going to settle, exactly. That's all it is. It's a simple physical process. And in the 30s, we've been doing this since the 30s, this primary treatment. So whatever settles, we pump out the solids that has settled into the solids processing, where the clear liquid overflows into the next process. And after that, this is where the biological treatment starts.
Yeah, and this is something that I think our viewers, both here and abroad, will find very interesting, because really you've gone now from the mechanical to the biological. as far as this process, because that's really where it is the aerobic and anaerobic bacteria now starts to do its work, correct?
Yep, exactly. It's way more cost effective to let the microbes, the tiny little microorganisms, do the work for us.
Yeah, and there's trillions of them. That's what people have no idea.
It's just a whole diverse ecosystem that's doing the work for us.
Yeah, and I tell you, this is really a beautiful layout, and this is some of the new improvements that you're doing. I mean, just since you've actually been there. So what are we seeing here in these colors, the blue, the green, yellow, and the pink?
Sure. So some of this is the blue is the expansion of the secondary treatment. So that's the biological system,
right? Where
we add a lot of air and we grow these beneficial bacteria that basically munch away at what we flush down the toilet. And these, in a way, sometimes these bacteria are kind of like you and I. The three things that they need are food, which is what we flush down the toilet, air, which we use a lot of energy to provide through these big blowers, and there's plenty of water.
Plenty of water.
Yeah.
Okay.
So and it's just providing more space and more upgraded equipment to be able to do their work.
And then green and yellow?
And the yellow is the nutrient removal. That's also in order to comply with this very stringent limit that we have to expand our existing facility.
Yeah. And then the green, we're going to talk about that in just a
Exactly.
little bit. In this, the biosolids is something we'll get to later, but I know this is really kind of your pride and joy as far as all this is going on, taking care of all this, and also to take that and turn it into useful products for DC Water itself, not just to send it out to the countryside, but actually turn this into electricity, and that's something we really want to spend some time on.
Yeah, absolutely.
Because that's very important. And if you're an engineer, this is all beautiful, these tanks and all that. So tell us about what we're seeing here.
So this is the thermal hydrolysis process. So this is in the construction phase. This was part of the $400 million biosolids program that we had completed a couple years ago.
Okay. And then we're going to get to all this later on, this hydrolysis. But looking at this, what do you see DC Water being in the next 5, 10, or 15 years as far as improving its processes and giving better, even better service to its ratepayers?
I think the biggest thing that we're pushing for is because some of the things you'll hear about later with the Clean River project, with the big tunnels.
Right.
We have invested a tremendous amount of resource into it. Right. So now, because the ratepayers are getting hit hard, we have to figure out how to optimize and make our entire organization more efficient.
Yeah. Well, when you look at this technology you have here, this is just absolutely incredible, and we're going to get to that in just a little bit. But this is Ryu Suzuki, professional engineer, manager, process engineering, DC Water. Water is life. Thank you for being with us as we create the Emerald Planet.
Okay, so we drowned the fire, stirred it, drowned it again, and now just feel if it's cold.
Yeah.
Cool.
Smokey just gave me a bear hug.
I know. Already posted it.
Creak in my neck, limp in my step, cramping in my muscles every time I try to flex. All of the ones get on. It's very sad that I can do was remember you. You know I usually say no, but if you throw me love, I'll throw you some more.
It's a big responsibility.
Oh, it's huge. I know, it's huge.
And the salary.
Oh my god, yes.
Right?
I mean, like, I was about to move in with my parents, and right before, so this saved me.
I really believe in you, you know?
Thank you. It's nice to hear that from someone.
These are cool. Did you, what did
we're back to the Emerald Planet. Here again, your host, Dr. Sam.
Hello, and welcome to the Emerald Planet as we come to you week to week looking at what we call the best of the best technologies, services, products, and the processes that are going on around the world. And many times, you know, we're exploring Asia and Europe and Latin America, African continent, all these places. But yet, you know, we have many of these best processes right here in Washington, D.C. itself. And one of these is DC Water, and this is called the most advanced wastewater treatment facility on the planet. And I'm very proud of that, and I talk about that when I'm traveling abroad. But we have someone that's going to talk to us a little bit about that and show us as if they were taking an actual tour of the facility of DC Water, which is in South Washington, D.C. And this is Ryu Suzuki. He's a professional engineer, PE, a manager of process engineering at DC Water. And water is life. I always have to put that in because that's in all your logos and your advertising. We can see that in the logo right there. But looking at the solid waste to energy, this is something that really is very new at DC Water. And actually, my understanding is now you've morphed to where you're taking and creating almost a third of the electrical power that you're using on this facility. So we're going to go through this. This is called thermal hydrolysis process. I'm just putting this up right now. We're going to come back to this image that we have here. But what is thermal hydrolysis?
Okay, what it is, it's basically a pressure cooking mechanism. So, you know, if you cook beans normally, it takes about 4 hours on a normal pot.
Right.
But if you pressure cook it, you could cook it in, what, 30 minutes?
Just about.
More or less. And that's exactly what we're doing with this enormous amount of solids that we have separated from the water, and now it's concentrated in this solid form. And we have to treat it before it could be land applied.
Now, this whole thing about resource recovery, that's that's the theme, although we're really looking specifically at this thermal hydrolysis process because of the international viewers as well. But we're looking at your site and we're seeing the scale model as far as this facility and as we're saying, putting theory into practice. Okay? So looking at your site and this mock-up here, where does all of this fit in? Because you look at the site as it was when I was just there, you know, a couple years ago now. I don't see how you could put anything else in there. I mean, this is just chock-a-block full. That's
the real estate is a major premium in our place.
And but looking at that, this is something that's been going on for a long time, going back at least a decade.
Oh,
because
absolutely.
when I was out there first time about 9 years ago, they were actually talking about this.
Yeah, so what happened was in around 2006, they had a bid out to construct 9 egg-shaped digesters, conventional digesters. And when the bids came back, they realized that the entire project was going to cost more than $600 million. And they had
That's real money.
Yeah, and they had about $400 million to spend on it. So they had to go back into the drawing board and to figure out the proper technology that allows us to meet our goals and still create this excellent final quality, which is the biosolids that we want to be able to reuse.
Now, looking at this is a very sophisticated process. What is driving this process? Because there's a lot of time and money just front end of this before you ever get to actually do the installation and, well, the design and installation of the equipment. What's driving all this?
I think it's just a combination of everything. It's the long-term, if you look at the long-term risk of like, to make sure you don't run out of places where you could apply the solids.
Right.
And also, so you got the long-term cost as well as just to be able to create this good product.
Yeah, but doesn't the regulators have something to do with this? Isn't that really one of the principal drivers behind all of this, to make sure that the water is coming out the cleanest possible?
So yes, on the liquid side, yes, we have put in enormous amount of investment to clean the water itself, but the byproduct is the solids. And that was actually not driven by regulation. That was all more based on looking at the long-term operational sustainability of DC Water.
Yeah, and that's really important. Sustainability, resiliency, and also innovation, because you really just scoured the whole world as far as finding the best technologies. So where did you actually get this particular technology that then you brought into DC Water? And now it's, I mean, it's an incredible process.
Yeah. So actually, this thermal hydrolysis, it's been going on in Europe for some time. The company is originally from Norway. This particular system that we bought, and now many other companies are getting into offering a similar product as well. So they've been doing it in Europe, and it seemed like it's the appropriate fit for DC water as well.
Yeah, an appropriate fit we're looking at now. This is in large because I've took over a lot of extra space out of your footprint out there. But tell us what we're looking at in this green and purple space.
Yeah, so this is most of the solids treatment process that we're going to be talking about in a little bit. And that's what we do is we take this tremendous amount of organic material and convert it into clean biosolids as well as renewable energy.
Yeah, and the whole thing about this is taking that. This is a waste. You've been shipping it. It's got to go by trucks. You're trying to find, land out in the countryside where it can go, but stay away from estuaries, the creeks and the ponds and the rivers and all that. It seems like you've really come up with a really excellent solution because you can, you're producing all this right there and you use it right there and you turn it into a kilowatt.
Yeah, well, that too. But originally, one of the biggest advantage of having an anaerobic digestion system is before what we did was all the solids that we added lime to it, raised the pH up to 12 to get this Class B. And we had to truck out about 60 trucks every day. So that was close to $19 million a year.
And the whole thing about it, just think about, the amount of greenhouse gases emissions from all those trucks that are running on the highways. We certainly have enough cars and traffic on the highways around Washington, D.C. We don't need more. We need less.
Yeah, absolutely. But with this new, with thermal hydrolysis / anaerobic digestion, we're converting half that solids into biogas, which is a combination of methane and carbon dioxide. And it goes into another combined heat and power facility where it gets converted into electricity and heat to drive the thermal hydrolysis process, which is the steam.
And
pressure cook the sludge.
Yeah, and this is really very efficient that you're doing, and I find this is absolutely amazing that maybe we waited so long to do this, but I guess the Europeans perfected this, particularly the Norwegians, and then we decided, well, this is something we need to really try here. Was that part of that process?
Yeah, absolutely. And once again, you talked about how there's limited real estate in our facility. So we needed to be able to a facility that could do all this treatment for us in a very small footprint. And that's what thermal hydrolysis allows us to do.
And this is some of the equipment that you're using this. What's this main process train? You and I were talking about this earlier. This is a beautiful layout. I like the color scheme and the scale and all that. But tell us, what does this really mean?
So the main process train is, it's basically, it's the main process train of the solids processing. And what it is not only does it include the thermal hydrolysis and anaerobic digestion, but all the other auxiliary systems that we need to be able to make this system work.
Now we have this here. This is a beautiful looking piece of equipment. Of course, if you like engineering and technology, this is beautiful. Other people would say something different. But the process of this, what would have been there before? Would it have been nothing, or would it have been much simpler and much less complex than what we're looking at right now?
So
just for the people that are looking at this, how have we morphed, we've gone to the next level as far as processing?
So anaerobic digestion, if you could think of, is this massive cow stomach that takes an organic material and stabilizes the solids and converts it into biogas.
Okay.
But say if you have raw food, which is raw solids, it takes a lot of space to be able to break it down fully, to get the full reduction of solids, to let the biology do the work. But say, if you could imagine, if you're able to cook, going back to the bean, if you have the cooked beans, it takes way less stomach volume to do the same amount of treatment.
So that way,
because it becomes way more biodegradable by cooking this material. And plus, another major advantage is because we're cooking it at such a high pressure, tremendous amount of pressure and temperature, you're sterilizing the solids. Because these solids do have a lot of pathogens in it, but at this high temperature, high pressure, you're just annihilating it all.
Yeah,
you're sterilizing
and you want to kill all that off. Now, dewatering, why is that so important?
Dewatering is because, we still have to haul out the material from our site to different gardens, farms, for a land application. And you want it to be as dry as possible because the more water you have, water is very heavy.
Right.
And right now the limit of
And
technology.
also too, you'd have those, those solids in. It's easier for them to, get into the streams, the ponds, whatever surface water that you have if it's really wet versus being dry and just spread across the top of the soil.
Yeah,
correct?
yeah, absolutely.
Yeah, because this is really a nutrient that the farmers are using.
Yeah,
Combined heat and power, this is something that you referred to just briefly before, but this is something that's really new there. So tell us why this, again, is so important as far as DC water is concerned, but also the ratepayers and to the environment, because that's really the ultimate, the ratepayers and the environment. How does this really help?
Okay, so in the digestion process, we generated all this biogas that has about 65% methane or natural gas. And first we clean it up, and then we compress it to a very high pressure, and then we combust it through this combustion turbines to generate electricity. So we're we're the largest energy user in all of DC area, and meets about 1/3 of our energy need. Yeah. Which is enough electricity to power about 8,000 homes is the typical.
8,000 homes.
Yeah, all from.
That's incredible.
Yeah, all from what we flush down the toilet.
Oh my gosh.
We're able to get, there's a lot of energy value in it.
Right.
Yeah, yeah.
Absolutely, and that's what we're using it for. And this is really just a schematic. It's what we were looking at much earlier as far as the layout of this whole facility. And but looking at the future, what do you see as far as this thermal hydrolysis process and where we're going over the next 5, 10, or 15 years? We go from 1/3 to half, 2/3, 3/4. Are you going to generate your own electricity and steam, or what do you see for realistically for the future?
For the near future, I think at least mine and our team's main goals is to really maintain and optimize the system, because there's a lot of moving parts, and our ratepayers have made a tremendous amount of investment. So it's our duty to make sure this system is sustainable and we're able to keep running it.
So process performance, curtain status, all of this is to take this, make it that much better. Yeah. And then if you can expand it gradually over time, you want to do that.
Possibly, but for now, our main focus is to maintain what we have.
That's fantastic. Ryu Suzuki, professional engineer, manager, process engineering, DC Water, Water is Life. And this is just incredible to take this tour through we'll call it a campus. It's a beautiful location, it's a beautiful site. Thank you as we create the Emerald Planet.
So, I just moved in with this family, and it's embarrassing. The little one, he likes to go outside and crawl around in the giant litter box. I don't know what he's doing. I mean, I was born and I knew how to use the litter box. Look at that. That's disgusting. Oh, poop already. You're making me nervous. Oh, okay, I can't look at this anymore. I really hope he grows out of this, for his sake.
So how was work?
It was 1,300 hours. My math class from 302 was in the trenches. Davy Roth had it the worst. Fractions were coming at him left and right. He just didn't get the damn things. 2 days ago, I tried to teach him what 1/4 of 1/2 was using different sizes of blocks. Yesterday, I tried again by dividing up pizza. Both missions failed.
Oh no.
But today, I was ready. I created a combat math game where the only way to beat the enemy is to out-fraction them. Davy conquered every last denominator. My game was so successful, the principal is deploying it to math squadrons all over the school. Anywho, how was your day?
Oh, today my boss treated the office to salad wraps.
Salad wraps.
No.
150 over 90.
180 over 111.
160 over 110. I had a stroke.
This is what high blood pressure looks like. You might not feel its symptoms, but the results from a stroke are far from invisible or silent. If you've come off your treatment plan, get back on it, or talk with your doctor to create an exercise, diet, and medication plan that works for you. Go to loweryourhbp.org.
If I would have followed a treatment plan, I would not be in this situation.
we're back to the Emerald Planet. Here again, your host, Dr. Sam.
Hello, welcome to the Emerald Planet as we're looking around the globe on the topic of water. Water is life, and DC Water in Washington, D.C. is the largest, most advanced solid waste water disposal unit in the planet. And at the same time, water is life, and so they're very serious about making sure that they are taking all of this, the solid waste that comes from Northern Virginia, Southern Maryland, Washington, D.C. itself, and then put the very best quality as far as the spent water back into the river. So we're protecting the Chesapeake Bay, all the tributaries, and all the way out to the Atlantic Ocean. So it's a huge chain right there. And sitting right next to me is Seth Charde, who is a lead AP, PLA, and he's a program manager for green infrastructure construction with DC Water. Water is life, and we're really glad to have you here.
Thank you.
And what I'm going to do, we have this logo behind us, and I always ask this question when I see this: what does this logo mean to you when you show up each day onto your campus? And how do you feel this responsibility all to the tens of thousands of people that, actually millions of people, that depend on you on a day-to-day basis?
Sure. I think it's something that many people actually take for granted, right? You come home, you turn on the tap, you flush the toilet. Water is the backbone of our everyday existence, and people often don't think about that. And so, taking into account, water is life. Well, it's obviously necessary for life. We can't live without it, but it's also just absolutely critical to, our lives in the district, our everyday lives in the city.
Yeah, and everything about us. But this looks very innocuous. It's just sitting there. But this thing is a monster that we're looking at right now. Now we're moving into this big dig, right? I love to call this, and I've heard that. I don't think it's original to me. But tell us about the big dig and what are we actually looking at in the size of this thing?
Absolutely. So we're looking at one of our tunnel boring machines. And so this is one of the machines that's cutting the tunnels that we're constructing underneath the district as we speak. And so we're building 18 miles of deep tunnels to intercept combined sewer overflow and capture that flow and keep it out of our waterways. The tunnel boring machine is typically about 450 feet long. They're assembled or they're constructed in Germany and then shipped over. At least this machine was built in Germany and shipped over in about 17 pieces. It cuts a 23-foot diameter tunnel.
That's
so
incredible.
It's a massive,
That's hard
massive
to
machine.
Yeah. And you look at this, and it's not that overwhelming as far as looking at it, but something that can cut 23 feet. I mean, that's huge.
I can tell you, as someone who's been down in the tunnel, or also someone who stood in front of the cutter head of these machines, it is absolutely staggering, just the sort of enormity of the machine itself. It's really just massive.
Now, looking at this, I mean, this all comes, there's a lot of regulations involved in this. We wanted to improve the rivers here, but again, going to the Chesapeake Bay, out to the Atlantic Ocean. I mean, there's a lot of people that are very concerned about the water it's coming into and then going out of Washington, D.C. in this whole region. But it's a long timeline. If you look at the number of years involved in this, it's incredible.
That's right. So we've been working on this project really since the late 90s. And so basically in the late 90s, the district and DC Water were found to be not compliant with water standards with these combined sewer overflows that were going into the creeks and rivers. And so by 2005, there was a consent decree and a long-term control plan. And the long-term control plan is basically the mechanism for meeting water quality standards. And the way that we're doing that is through these deep tunnels, as well as green infrastructure, which is something we'll talk about a little bit more later.
Yeah, and we have the schematic. Just tell us what we're actually looking at here and why this is so different, maybe even radical from what was going on before.
That's right. So in the schematic, you can see the old sewer system and the old outfall that goes right into the river. It's showing a combined sewer. So the middle third of the district is actually a combined sewer system. So it's one pipe for both the sanitary flow and stormwater flow that's coming off the streets.
Which is very inefficient.
It was actually high tech about 120,
I was going to say 125 years ago, but now no longer.
That's right. It replaced open canals and the and cesspools behind people's homes. But we know better now, and obviously we don't want to combine those two, the sanitary and the stormwater. And the challenge with these old systems is that when it rains too much, there's not enough volume inside the pipe, and they actually overflow by design into our creeks and rivers. And so looking at this schematic, what it's showing is essentially a diversion structure and then a new tunnel that we're constructing. And that diversion structure pulls the water that would have otherwise gone into our river into the diversion structure and directs it down into the tunnel where we can convey it down to Blue Plains to clean it up.
Yeah, and that's the main facility. And this is a bird's eye view of all this. And now we're looking at this massive hole that's been opened up in the ground. You're going through neighborhoods. And of course, this is very disruptive to, not only just this neighborhood, but the traffic and the whole city. So how do you lessen some of this, but yet have people understand this is critically important for everyone's future?
Right, right. So this particular project is the First Street project. And we actually advanced this construction. This was originally supposed to take place in a few years. The neighborhood has been historically receiving flooding during high rainfall, and it's a result of undersized pipes that are also part of the combined sewer system. So we advanced this part of the project, and the First Street project was in particular a little tighter than some of the other projects or other tunnel, the aspects of the tunnel project that we've been constructing.
Yeah, and we're going back to this massive unit, and let's see if we can get back to this. This thing has got to go down through here. Is that what I understand, or how does this actually this monster get into this?
Okay, so what we're looking at First Street is actually a drop shaft, and then some of the work to build the diversion structure. The tunnel itself and the tunnel boring machine was dropped north of this point in another drop shaft where we had a little more room to work. The staging areas for dropping the tunnel boring machine are a little bit bigger than what you see on the First Street site. Yeah.
Well, looking at this gives you an idea of just how huge this is, and we have a human in front of this, and we kind of and we see those in the back. I mean, this is massive.
Absolutely massive.
And all this is going on under the city, and there's going to be multiples of these, correct?
That's right. So these tunnels are being dug anywhere from 100 to 150 feet below ground. Again, it cuts a 23-foot wide interior diameter tunnel, which is bigger than the metro tunnels. And we're building 18 miles of tunnel. So 13 on the Anacostia Blue Plains side, and then another 5 on the Potomac side.
Yeah, this is just amazing. Tell us a little bit about what we're seeing here, not to be too technical, but just kind of how all this works together. And you're doing, would you say 100, 150 feet below the surface?
Below grade, that's right.
That's incredible.
So part of the challenge is, the sewer system is not 150 feet below grade. And so we have to convey that flow down to the tunnel. And we need to do it in a way that basically reduces the amount of air that's in the water, because air takes up space. And so what we're seeing is part of the diversion chamber or diversion structure, which directs the water from the existing sewer and then brings it down to the bottom of the shaft and into the tunnel, while reducing the amount of air that's in that flow.
And this is all part of that process we're looking at here.
That's right.
Yeah.
A similar aspect.
Now, looking at this is all, is this precast concrete? Is it poured to site? How does all this work? Because we get a lot of questions. That's why we've been trying to get you on the program for so long about how this thing really works. People see it, but they don't know exactly what it is.
Right. So the drop shafts, the diversion structures, most of those are cast in place, cast on site. The tunnel segments are all precast, and so it's 7 segments for each ring. And those are precast, off-site, actually not too far from here, but they're trucked in, and then we bring those out to the face of the tunnel boring machine on a little train. There's an arm at the end, a robotic arm that picks up those segments, puts them in place, and then the sandhogs, the crews that operate the machine, get up and bolt those segments into place to finish one ring.
This is incredible. Now, this is a composite of 3 different photographs, so we're looking at multiple parts here, and as we say, this really is moving parts. So tell us a little bit about this.
Sure. So the smaller circular hole you see there, that's an adit, and it's basically a connection between one of the existing sewers and into the tunnel. And then the other component is an existing sewer with a weir, as we're seeing the inside of the diversion structure. So again, when we have high flow conditions, the weir allows that flow to pass over the weir, get into the diversion structure, and then make its way down into the tunnel. Otherwise, the flow would stay within the channel of the existing sewer system and then go down to Blue Plains as it would in dry flow.
So all this money the ratepayers are putting into this, and the bondholders and all that, they're already seeing benefit from this, correct?
Absolutely. So the first segment of the tunnel has been constructed. That's a Blue Plains segment, and that was put into operation in March of this year, March 20th of this year. And since March, or within 4 months, we've kept over 2 billion gallons of combined sewer.
2 billion gallons with a B.
That's right.
That is absolutely incredible. And I understand there's just thousands of tons of trash that's been siphoned off as well.
About 130 tons of trash.
That's just incredible. And what we're looking at here, this is something that was, 1892 is one of these old chambers, and then we're doing all this new work around it. And we're just going to put some of this in here. But the last question really is the big dig. What do you see the advantages of that expanding and really helping the city, the environment, Chesapeake Bay, the Atlantic Ocean, and the ratepayers over the next 5, 10, 15 years?
Well, it really comes back to fishable, swimmable rivers, and
so that's
and bay
really is the
restoration.
key.
Absolutely, yeah. So meeting water quality standards, having safe, fishable, swimmable rivers, and then obviously bay restoration and the economic engine that the bay is for the region.
Yeah. So what is your hope as a professional doing all of this? And we're going to talk about green infrastructure and all that, but as far as the big dig, what is your hope for this, and what are you actually seeing? And then we have to get off.
Well, so the tunnel is engineered to have a 100-year design life, but given the quality of the construction, the quality of the tunnel, I think we're going to see more of a 200 or 300-year design life.
That's absolutely incredible. And we go back to, we saw that those tunnels going back to the 1800s. I mean, they've lasted. It's new technology, and it's a new life as far as the environment. Seth Charde, Program Manager, Green Infrastructure Construction, as we create the Emerald Planet.
And I can't change, even if I try, even if I wanted to. My love, she keeps me warm. 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 She keeps me warm.
We are neighbors and best friends.
I love my sister.
My heart doesn't see race. Love is love.
Our family is no less than any other family.
Open road, here comes the Heffley family. Whether it's a short trip or a long haul,
Estimated time, 47 hours.
they will beg,
You're hungry? I'm happy to provide.
they will plead.
Deep fried butter on a stick.
But whatever you do, don't wimp out.
Now you're talking.
Make them buckle up.
He can't hurt.
Remember, safety first. Cheese curls second.
Are you orange?
Eva Marie smoked 12,000 packs of cigarettes over 15 years. She quit, and now there's a new lung cancer screening that could save her life. You stopped smoking. Now start screening. No matter how much you smoked, early detection could save you. Talk to your doctor or learn more at savedbythescan.org.
We're back to the Emerald Planet. Here again, your host, Dr. Sam.
Well, welcome to the Emerald Planet TV. We come to you on a week-to-week basis from Washington, D.C. in the United States as we look around the globe in 144 different nations looking for what we call the best of the best technology, services, products, processes, and the people, of course, are making a difference as we move through the 21st century. And as we have about 9 billion people on planet Earth by 2050 and maybe 12 to 13 billion by the end of the century, how we're going to provide everything that people need, but specifically water. And a gentleman sitting right next to me is actively involved in that. This is Seth Charde. He is a PLA, lead AP, all these mean important things, program manager for green infrastructure construction for DC Water, Water is Life. And I love this tagline because you see this absolutely everywhere. So people know this and they remember that, and it's in your logo right in front of us. But we just looked at the big dig, these huge machinery, all this advanced technology, but what you really focus on is green infrastructure.
That's right.
So you're melding all this technology, this advanced equipment, into something it's a very lovely process when you see it all over Washington, D.C. So why take all this technology? We're spending $2.7 billion to do all these tunnels and diversions and all that. And now we're putting more and more into green infrastructure. Why are we doing that?
Sure. Well, it really comes down to triple bottom line, right? So the gray infrastructure, the big tunnels, they're incredibly effective, but they're also 150 feet below grade, out of sight, out of mind. And we wanted to introduce solutions that also carried other benefits, right? So offered the opportunity for local green jobs, or greening up neighborhoods and helping to promote neighborhood redevelopment. And so we can really see that with green infrastructure.
Yeah, and the whole thing about this green infrastructure, my understanding is we're already above 35, maybe 37% canopy, meaning trees, all over the city. And of course, we have a lot of grass. Rock Creek Park is a giant carbon sump, as we know. So it's very important that we have this to complement all this high technology you have. But let's go through the pervious, impervious, and then we're going to lead right into what you're actually doing as far as this green infrastructure, and we'll see some of that.
Sure. So despite having all these trees and despite having Rock Creek Park, much of the district is impervious surface. So that's roadways, rooftops, sidewalks, parking lots. And so, in a pre-development scenario, when it rains, the water soaks into the ground. You don't have very much runoff at the surface. You have more evapotranspiration. In a post-development situation, especially in an urban area where you may have up to 75% impervious surface, that water has nowhere to go except to run off on the surface, go into our sewers, go into our creeks and rivers. So you see a huge spike in volume, and you don't see that groundwater infiltration. And so what green infrastructure does is really try to mimic the pre-development conditions that were there before the city was constructed.
Yeah, and looking at this as far as the sewer systems, we got this overview and these 4 different drawings here. How does this really relate to Washington, D.C., the ratepayers, but also downstream, no pun intended, as far as the quality of water and what's ending up in the Chesapeake Bay and then, of course, into the Atlantic Ocean?
Right, right. So the district, like many older municipalities in the United States, has this combined sewer system, and this is a legacy system. So in dry conditions, flow stays in the pipe, and it goes down to Blue Plains where it's treated and cleaned up. And when we have too much rain, there isn't enough volume in that single pipe because it's a mix. The combined sewer is a mix of sanitary and storm flow, and it overflows by design into the creeks and rivers. And of course, introducing raw sewage into our creeks and rivers is not healthy for our immediate community or any of the downstream communities.
Yeah, and the whole thing about this, and I'm going to stop at this this diagram right now, because people don't realize the damage that the increase as far as the rainfall. And now they're saying we have a margin of maybe a third more volume, third more violence, and people are actually, scientists are using this term, that's coming because of these cloud bombs and all this change because of climate change is going on. And so it's destroying the riverbanks, and it's just doing real damage to the environment.
That's right. These huge spikes in flow are really unprecedented. And so you're seeing exactly what you're saying. You're seeing scouring of the stream banks that's picking up a lot of sediments. It's transporting that sediment through the aquatic systems and destroying aquatic habitats, polluting the rivers, polluting the bays. And so by holding that flow back, keeping it out of the creeks and rivers, using green infrastructure, we can really try to reduce some of that sediment and pollution.
Now, going to this Clean Rivers project, when we talk about these, the big dig, and I put this up, I didn't use it in the last segment, but I wanted to put it here. This shows there's a tremendous investment, and then we're going to go into your green infrastructure.
Right.
But how does that then, no pun intended, flow right into what you're doing as far as your green infrastructure? How do these two fit together? Because you got the huge technology,
right,
and then you've got just beautiful streets.
Right. So the map we're looking at shows the tunnel system as well as the target areas for green infrastructure. And so on one side, on the right side of the map, that's the Anacostia tunnel system. And then on the left side of the map, that's the Potomac tunnel system. We were looking at the volume of flow and then also looking at the timing of implementation, and made a decision about pursuing the tunnel-only option on the Anacostia side. Looking at the flows and the existing conditions that we have, green infrastructure made a lot of sense for the Rock Creek portion.
I see.
And then also the Potomac portion, or the northern Potomac portion of the watershed.
Yeah, this is called bioretention. What is bioretention? And we have probably 4 or 5 slides, and let's just kind of step through these and how they're different, but also they really go to the same benefit and the same purpose.
Right. So bioretention is one of the sort of suite of practices, of green infrastructure practices that we're using. Essentially, we are mimicking natural processes. It's constructed by excavating out about 4 or 5 feet. You backfill with gravel, which creates a storage area for holding water. And then on top of that, you put a very sandy planting soil, and then you plant out the top. So from the surface, it looks like a garden. Sometimes these are called rain gardens. But from a functionality perspective, it can really bring in a lot and store a lot of water that's coming off of our streets and rooftops. And it infiltrates that water down into the ground or slowly releases it back into the sewer system after the storm has passed.
Now, I've heard over the last couple of decades that the Potomac River has been, the amount of inflow is coming in is about 4% less per year. Now, I haven't verified that. But having this, now we're actually capturing that. Now we're increasing the water table, throughout the district. Is that going to help as far as the flow, both for the Potomac and then also for the Anacostia?
So we're not anticipating any increase in ground flow. In fact, we are constructing all of our facilities connected to the combined sewer system.
I see.
And then using a flow restriction device to slowly release that water off. Where we can infiltrate, we will. But that's not necessary to the functionality of the system.
Yeah, John from Fairfax is calling in about, again, this retention. He's really interested about why you're using plants and then, of course, the gravel, the sand. But it looks like there's pipe in here. What is this pipe doing, and does that go to the point of you're actually putting this into this new system?
Right. So in the facilities that we're constructing, we always have an underdrain, and we use a flow restriction device. And we're connecting that back into the combined sewer system. So imagine like a storage tank with a very small hole. It lets out a very small amount of water at a single point in time. So we can fill up the bioretention. The storm passes, the capacity in the pipe in the street empties out, and then we can slowly release back in after that storm has passed. So the plants also, back to the question about the plants help to filter and clean the water as well. So it gets cleaned up within the bioretention before it goes down into that aggregate storage bed.
Yeah, and I think if John looks at this, you can see exactly what you're talking about, whereas the little tiny hole that's coming out through this pipe, and it's just slowly releasing this. But going to this permeable pavement, what is permeable pavement? We're starting to see this all over Washington, D.C. I do a lot of walking, and as I walk around the city, I'm seeing more and more of this.
Right. So permeable pavement functions very similarly to bioretention. The main difference is, obviously there are no plants. So from the surface, it looks like any pavement, like a cobble or a concrete or an asphalt. But again, we excavate out, we put down a gravel storage base, and then a little bit of a smaller gravel on top of that as a setting bed. And then we either place precast pavers or bricks, or we do a porous concrete or a pervious asphalt on top. The porous surface allows rainwater to go through that surface down into the storage base where it's held for a period of time and either infiltrated into the ground or again released back into the sewer system.
Yeah, John, our viewers can see this. You have one that's impermeable, asphalt, and then you look at the pavers here. And when you're walking down the streets, because I have to walk the dogs, and so I'm out there when it's really downpouring, you can actually tell the difference when you go alleyway to alleyway or street to street because of that.
Right, you can, in a rainstorm, you might walk down one of these alleys, and the noticeable difference is that you don't see water flowing through them. It goes immediately down into the pavement surface. These pavement surfaces typically have an infiltration rate of around 60 inches per hour.
How much?
60 inches per hour.
Oh my goodness, that's absolutely incredible. And now we're looking at what this really looks like. You've been describing this for us, so let's go over this. We're about running out of time, but so John and many others will know exactly what we're talking about.
Right, so this picture is showing one of our permeable pavement facilities being constructed in the alleyway. What's nice about this picture is you see a lot of the elements, right? So you see the excavation, you see the underdrain, you see a check dam, which helps us manage the slope and manage the water within the facility on a slope. And then you see the various layers of aggregate behind it, and then some of the clean-out structures. Of course, when this was ready to be paved, we just put a pavement surface across the top.
Sure. Looking at this, and I wanted to leave this up here as far as this rain garden, because I think these really are pretty, and you're seeing more and more. But looking at as far as this green infrastructure, what do you see for controlling stormwater runoff over the, say, the next 5, 10, or 15 years? Are we going to see more and more of this, and is it going to be in all the neighborhoods, or what are we going to see? And we got to be quick.
Right, so you'll see more of it in all of the neighborhoods, but those are under other regulations that are being applied district-wide. You will definitely see more of it within our green infrastructure areas, as we're still constructing our first projects, and we have about 12 more years to finish out the overall program.
That's incredible. This is Seth Charde. He's the program manager, infrastructure and construction, as we create the Emerald Planet.